Welcome to Advanced Topics in Artificial Intelligence and Machine Learning, PhDAI730, Lecture 5. This is your Professor Atif Fareed Muhammad. We will delve into advanced topics in machine learning and artificial intelligence, with a particular emphasis on kernel methods and Gaussian processes and their significant applications in the field of artificial intelligence. Kernel methods are essential in modern machine learning for their ability to handle complex data structures by transforming them into higher dimensional spaces. This transformation enables algorithms to find intricate patterns and relationships within the data that would otherwise remain undetected in lower dimensional spaces. By using Python, a leading programming language, as you all know, in artificial intelligence, we will implement kernel methods to enhance machine learning models, permitting them to perform complex analysis and make accurate predictions. Libraries such as scikit-learn will be instrumental for you all in applying these methods, providing tools to efficiently compute kernel transformations and build robust models. Why advanced AI and machine learning? That's a great question. Modern AI requires handling complex, high-dimensional data. Kernel methods and Gaussian processes are powerful tools for such tasks, used in recommendation systems, bioinformatics, finance, and more. What are kernel methods? Now let's look into this in a little bit more depth. Kernel methods are a powerful set of techniques in machine learning that helps computers understand complex patterns in data by transforming it into higher dimensional space. Imagine you're trying to sort two piles of mixed up red and blue marbles on a table. If you look at them from above, they might overlap and seem impossible to separate. But if you pick up the table and tilt it, suddenly the marbles might separate into two clear groups. Kernel methods do something similar. They tilt or transform the data into a space where patterns become easier to spot without actually having to calculate all the complex math involved in moving to the higher dimensional space. Let's take robotics as an example. In robotics, kernel methods are often used to help robots learn from sensory data, like images or sensor readings. For example, suppose you have a robot arm that needs to classify different objects on a conveyor belt, like separating apples from oranges. The raw data from the robot's camera might show color and shapes that overlap, making it hard to tell the fruits apart. A kernel method can transform this data into a new space where apples and oranges from distinct groups, permitting the robot to sort them accurately. This transformation is done efficiently using something called a kernel trick, which avoids heavy computations. Kernel methods are especially useful in robotics for tasks like object recognition, path planning, and even predicting how robots should move. For instance, if a robot needs to navigate a room full of obstacles, kernel methods can help it learn the safest path by transforming the map data into a form where the best route becomes obvious. This way, the robot does not just follow pre-programmed instructions. It adapts and learns from its environment, making it smarter and more flexible. The kernel trick, as just mentioned, avoids explicitly computing high-dimensional transformations, computes similarity between data points efficiently. The example is linear data becomes separable in higher dimensions. The common kernel functions. Now let's look into each of this in a little bit more depth. Linear kernel is the simplest type of kernel used when the data can be separated by a straight line or a flat panel at a flat plane or high dimensions. It works by calculating the dot product between two data points, which measure their similarity based on the angle and direction between them. For example, if you are training a robot to distinguish between two types of screws based on their length and width, a linear kernel might be sufficient if the screws from two distinct clusters that can be divided by a straight line. While it is fast and easy to compute, it is limited to problems where the relationship between their points is linear. In robotics, this kernel is often used for basic classification tasks like sorting objects with clearly defined features. Whereas polynomial kernel is used when the relationships between data points is more complex and linear but still follows a curved pattern. It transforms the data into higher dimensional spaces by adding polynomial features, permitting the model to fit non-linear boundaries like curves or spirals between classes. For instance, if a robot needs to recognize handwritten digits, a polynomial kernel can help capture the curved shapes like numbers, for example 3 or 8, that a linear kernel might miss. By adjusting the degree of the polynomial, you can control technically how flexible or wavy the decision boundary becomes, making it versatile for modularity as well as moderately complex patterns, the modularity maintenance in robotics, like gesture recognition or trajectory planning. If you're speaking with a robot and robot can actually return the favor and talk to you back. So like the Sophia Hansen of Hansen Robotics or Ameka, you might have seen these robots on YouTube and all those places. The Gaussian kernel, however, is also known as radial basis function or RBF kernel. It is one of the most powerful and widely used kernels for handling highly complex and nonlinear data. It measures the similarity between data points based on their distance from each other, creating decision boundaries that can be infinitely flexible. Imagine a robot trying to navigate a cluttered warehouse where RBF kernel can help it distinguish between safe and unsafe paths by capturing intricate patterns in sensor data. Even if the obstacles are irregularly shaped, this kernel is especially useful in robotics for tasks like training the maps of a certain terrain, object detection, and adaptive control where the relationships in the data are too complex for linear and polynomial methods. It is the ability to model subtle variations makes it ideal for real-world scenarios where precision is critical. Hopefully this has given you a little bit understanding of common kernel functions. Where are kernel used? As discussed, 3, 8, 4 are numbers, image classification, text categorization, bioinformatics such as gene expression analysis, and financial forecasting. Let's look into this with one example in a little bit more depth. Kernel methods are widely used across various fields, especially where data is complex and traditional linear methods fall short. In machine learning and artificial intelligence, kernels are the backbone of algorithms like support vector machines or SVM, Gaussian processes, and principal component analysis, also known as PCA. For example, in image and speech recognition, kernels help computers distinguish between different patterns, such as identifying faces in photos or recognizing the spoken words. They are also crucial in bioinformatics, where they analyze genetic data to identify disease markers or classify different types of cells. In finance, kernels assist in predicting stock market trends or detecting fraud by uncovering hidden patterns in transaction data. Essentially, kernels transform raw data into a form that makes it easier for algorithms to detect relationships and make accurate predictions. In robotics and automation, kernels play a vital role in enabling machines to interpret sensory data and make intelligent decisions. For instance, kernels help robots in autonomous navigation by processing data from sensors to recognize obstacles, match environments, and plan safe paths. They are also used in industrial information as well as automation, where robots classify defects in manufacturing or sort items on assembly lines as discussed earlier based on the visual or sensory input. In the healthcare robotics, kernels assist in analyzing radical uh, details in a medical image, such as X rays or MRIs, to detect abnormalities or assist in surgical planning. Even in agricultural robots, kernels help drones and autonomous tractors identify crops, weeds, or soil conditions by providing a way to handle non-linear and high-dimensional data. Kernels make robots smarter, more adaptive, and capable of performing complex tasks in real-world environments. The SVM kernels help the support vector machines classify nonlinear data. The example is handwritten digit recognition. I'll not go in much detail for SVMs because this is the in-depth discussion on the advanced machine learning methodologies. So support vector machines, I would suggest you to conduct a little bit research in your own time to understand that where SVMs are utilized and how that helps grow our learning in the machine learning and artificial intelligence domains. Let's look into Gaussian processes in a little bit more depth. GP. So the Gaussian processes has another name as GP. The GPs are transforming healthcare. Let's look into GP in more depth in the healthcare domain by providing powerful tools for modeling complex, uncertain, and noisy data. The common challenges in medical research and clinical practice it can also come under the domain of GP. In healthcare, GPs are particularly valuable for personalized medicine, where they help predict how individual patients will respond to treatment based on their unique genetic lifestyle and clinical data. For example, GPs can analyze patients' records to forecast disease progression, such as predictions or predicting how a diabetic patient's blood sugar levels might fluctuate over time. This probabilistic approach not only delivers predictions but also quantifies uncertainty, permitting doctors to make more informed and cautious decisions. By integrating data from wearables, electronic health records, and lab results, GPs enable tailored treatment plans that adapt to each patient's evolving health status. Another critical application of GPs in healthcare is drug discovery and clinical trials. Developing new drugs is a costly and time consuming process, often involving countless experiments to determine efficiency and efficacy as well as safety. GPs accelerate this process by modeling the relationship between drug dosages and patient responses, identifying optimal usage with fewer trials. For instance, in early phase clinical trials, GPs can predict the most effective and least toxic dose of new cancer drug, reducing the need for extensive human testing. This not only speeds up the drug development but also minimizes risks to participants. Additionally, GPs are used to optimize the design of experiments, ensuring that resources are allocated efficiently and insights are gained faster. GPs are also making waves in remote patient monitoring and predictive diagnostics. With the rise of telemedicine and IoT enabled medical devices, GPs analyze real time data streams such as heart rate, blood pressure, and oxygen levels to detect early signs of deterioration in chronic disease patients. For example, a GP model could continuously monitor a heart failure patient's vital signs and alert healthcare providers before a critical event occurs, enabling timely intervention. In diagnostics, GPs assist radiologists by providing probabilistic interpretations of medical images, such as identifying tumors in MRI scans while accounting for uncertainty. By combining predictive accuracy with transparency about confidence levels, the GPs are enhancing both the precision and reliability of healthcare technologies, ultimately improving patients' outcomes and operational efficiency as well as efficacy. The methods behind GP is assume data points are jointly Gaussian distributed, predictions are smooth, and include uncertainty estimates. The kernels in GPs define the covariance structure of the data. The common kernels are squared exponential, the metron, and the rational quadratic. I would strongly suggest you to conduct a little research on these to understand a better way for you to apply the kernel's utilization in the Gaussian processes. Why use GPs? Provide uncertainty estimates as mentioned in the healthcare example, flexible and interpretable. So if the change happens in the remote patient monitoring, the alerts can go to the PCPs or the principal care providers. That will take care of you using the telemedicine practice. Work well with small data sets because usually the blood pressure and the blood sugar data is not that bigger of an individual. Real world use cases, robotics, as we have discussed in quite depth, or the path planning is one of the main area which I have explored in the discussions earlier. Environmental modeling for the climate data is significantly important, and drug discovery, as we discussed in quite depth, that how drug discovery can be benefited by utilizing the Gaussian processes. Kernel methods versus Gaussian processes. The kernel methods focus on transformation and classification. Gaussian processes focus on probabilistic modeling and uncertainty. Let's look into the synergy between kernels and GPs. The synergy between kernel methods and Gaussian processes is revolutionizing path planning for robots. Let's take robotic world again as our example. Enabling robots to navigate complex and uncertain environments with greater precision and adaptability. Kernel methods excel at transforming raw sensor data such as LiDAR scans, camera images, or proximity sensor readings into higher dimensional spaces where patterns and obstacles become easier to distinguish. For example, a robot exploring an unfamiliar warehouse can use kernel-based techniques to classify different types of obstacles or identify safe pathways based on sensory input. When combined with GPS, the transformed features allow the robot to not only map its environment but also model the uncertainty associated with its sensors and movement. This means that robot can predict potential collisions or unstable terrains while accounting for noise in its sensors, leading to safer and more reliable navigation. In practical application, this synergy allows robots to optimize their paths in real time while adapting to dynamic changes in their surroundings. For instance, a search and rescue robot operating in a disaster zone can use GPS to model the terrain's roughness or stability, while kernel methods help it distinguish between traversable paths and impassable debris. The GP provides probabilistic predictions about the safest route, and kernel ensures that the robot interprets sensory data accurately even in cluttered or poorly lit conditions. Together, these techniques enable robots to make informed, uncertainty-aware decisions, balancing speed and safety. This combination is particularly valuable in fields like autonomous drones, self-driving vehicles, and industrial robotics, where real-world conditions are often unpredictable and require both precision and adaptability. The potential pitfalls: computational complexity, scaling with data size, choosing the right kernel hyperparameters, selection, overfitting in high dimensional spaces. As I just mentioned about the real life or real time data sets looked by robots to make an informed decision. The future trends: scalable kernels for big data, deep kernel learning, combining deep learning and kernels, the GPs in reinforcement learning. So I strongly suggest you to conduct a little research on Google Scholar or IEEE Explore, or use a library to find these topics and conduct a little research in each with an example for your learning. This will allow you to go and find out that how these are utilized in the industry. The key takeaways of this lecture are: kernel methods transform data for complex pattern recognition. Gaussian processes model uncertainty and provide probabilistic predictions, as mentioned earlier. Both are powerful tools in modern artificial intelligence. And before I close this discussion, I can share with you a real life thing that I had a chance to work with one of my classmates in my second doctorate. The gentleman's name is Jeremy Straub. He's also a professor of cybersecurity. So we have conducted a research on autonomous drone navigation in urban disaster response. To understand this scenario, so in case of a given natural disaster such as earthquake, a search and rescue team deploys an autonomous drone to survey a damaged urban area. The drone's mission is to locate survivors, identify hazardous zones like gas leaks or unstable structures, and map safe paths for rescue teams. However, the environment is highly unpredictable. Debris block pathways, winds affect the drone's stability, and sensor data from cameras, LiDAR, and thermal imaging is noisy and incomplete. Traditional path planning algorithms, which rely on fixed maps or simple obstacles avoidance, struggle to adapt to these dynamic conditions. The drone must navigate efficiently, avoid collisions, and prioritize area with high likelihood of survivors, all while accounting for uncertainty in its sensors and ever-changing landscape. I also had a chance to work with a city, I'll not name the city for the confidentiality reason, with their fire chief, and there's a publication under our name is there, and that was for the application of this research that I just shared with you in a little bit more depth. So the kernel methods for data interpretation, where the drones use these methods to process and classify raw sensor data. For example, a Gaussian RBF kernel helps distinguish between different types of obstacles, fallen debris versus intact buildings by transforming the data into high dimensional space where patterns become clearer. This permits the drone to recognize and categorize objects in real time, even if they are partially obscured or appear in unfamiliar configuration. So last not the least, by leveraging the synergy between kernel methods and GPS, the drone navigates the disaster zone autonomously, adapting to the new obstacles and prioritizing rescue efforts. Effectively, this approach not only improves the speed and accuracy and search and rescue operations, but also enhances the safety of both the drones and the rescue teams. The probabilistic nature of GPS ensure that the decisions are made with confidence, while kernel methods provide robustness needed to handle real world complexity as we have been discussing in quite details. So happy learning. See you in the next lecture.